Hi, this is the homework for this week. It's the Lewis structures. I heard from Dr. Valdez that you've had the Lewis structures in the lab, and I'd like to give you some more practice about this because this will be important for your next course, Chem 101. To access the problems, you'll have to go to the Chem 101 website, and that website is at chem101.co. I have a link for it in the canvas here for you. There it is. It's 101edu.co. Yeah, 101edu.co. If you just type chem101.co, your browser will figure out that it needs to be going to 101edu.co, and then you just launch that, and you'll find the homework there. The homework is due on Friday. This is how you do the homework. First, you'll have to figure out how to do Lewis structures, and you can use the knowledge that you gained from Dr. Valdez's lab course last week. And you can also watch this video, which I've posted for you, and read this part of the textbook, which I've also downloaded and posted for you there on the canvas. To use the app, however, there's a little bit of playing that you have to do. So the red atom, the red circle, is the active atom, and for H2CO, I'm going to have to make one of these a C. You're going to find from the videos and from your reading that the atom that goes in the middle of your Lewis structure is the first atom you see in the formula, except if the atom is H. H can never go in the middle. Now, the reason why H cannot go in the middle is because H can only make one chemical bond. However, if you have an atom in the middle, of course, it's making more than one chemical bond because it's in the middle, right? So I'm going to change this element to a C, right? So that changes the red element to a C. Red is just the active element, the one that I'm working on right now. So C is the first element here that in the formula, which is not H. All right. Now, why is it that the first element, which is not H, goes in the middle? It's because the first element is usually the least electronegative element, and the electronegativity is. Let me show you the periodic table. Electronegativity is just the force of attraction, or the tendency of an atom to attract electrons in a chemical bond, and as you go down any given column on the periodic table, if you just go down the column, the electronegativity decreases, meaning carbon has a higher tendency to attract electrons in a chemical bond than silicon does. Silicon has a higher attraction than germanium does, and germanium has a higher attraction than tin does. Tin has a higher attraction than lead does, and so on. As you go to the right in any row, the force of attraction, or the electronegativity in a chemical bond, increases. So bromine has a higher attraction for electrons in a chemical bond than selenium. Selenium has more attraction than arsenic. Arsenic has more attraction than germanium, etc. So that's electronegativity. Now, the way you draw the Lewis structure in the app is like this. So this atom is going to be the O, right? So I'll change it to O. And I'm going to add another bond. I'm going to go back to the C because C is the central atom, and I'm going to add another bond here. Right? So there's going to be an H here, an H there. All right. And I'm going to go back to the C because it is the central atom, and I'm going to add another bond. All right. So that's an H. Okay, so I'm done. I've got, that was wrong. Here, let me change that back. So that's a C. The central atom has to be a C. You got to highlight the new atom in order to change that one. So it's the red atom that is always the active atom. So now let me make the carbon active again. So I'm done. This is my Lewis structure for H2CO, or formaldehyde. Except I'm not done, because there are several steps involved in drawing a Lewis structure, as you've seen in the textbook and in someone else's video. You need to count the number of valence electrons total. So let's have a look here. Hydrogen on the periodic table is in the first group, so that's one valence electron. Carbon is 4 away from the end. 1, 2, 3, 4. So carbon has 4 valence electrons, and oxygen is 2 away from the end. So 8 minus 2, that's 6. This has 6 valence electrons. You could think of it as O has 6 valence electrons because it's in group 16. Carbon has 4 valence electrons because it's in group 4. And hydrogen, carbon has 4 valence electrons because it's in group 14, and hydrogen has 1 valence electrons because it's in group 1. You could also think of it as 8 minus. So carbon has 4 valence electrons because it is 4 away from the end here. 1, 2, 3, 4. And 8 minus 4 is 4. That's the number of valence electrons. O is 2 away from the end here. 1, 2. And 8 minus 2 is 6. So O has 6 valence electrons. This method of counting valence electrons is different for the positive ions, which are over here. These are elements that prefer to become positive ions, than for the negative ions over here. These are elements that they prefer to be negative ions. Actually, the metals are most of what you see on the periodic table. Everything here is a metal, except for these blue guys, these brown guys, and these gray guys. Everything here is a metal. These light blue guys over here, these guys are metalloids, so they are similar to both metals and nonmetals. But all of this other stuff, these are metals. These metals become positive ions. And the way you count valence electrons for positive ions is everything here has 1 valence electron. Everything here in the second group has 2 valence electrons. And everything in these other groups here, these have a variable number of valence electrons. Now, for the nonmetals, it's that 8 minus rule. So carbon is 1, 2, 3, 4 from the end. 8 minus 4 is 4, so that's 4 valence electrons. O is 1, 2 from the end, and 8 minus 2 is 6, so that's 6 valence electrons. So that's how you count valence electrons. We've got to add them all up. So let me get the calculator here. So we've got 2 times 1 valence electrons for hydrogen, plus 4 valence electrons for carbon, plus 6 valence electrons for oxygen. That's a total of 12 valence electrons. That's good. So I need to make sure there's a total of 12 valence electrons in this structure. 2, 4, 6. Every bond is 2 valence electrons. See, there are only 6 valence electrons here, so that's not enough. That means I'm going to have to give everybody an octet. So everyone has to have 8 valence electrons. So this carbon has to have 8 valence electrons. Oh, that's too many. Okay. Now that's too few. I mean, that's still too many. Okay, there we go. Now the carbon has 8 valence electrons. See? 2, 4, 6, 8. And this oxygen needs to have 8 valence electrons. Okay, see? 2, 4, 6, 8. So I have followed the rules of chemistry. Everyone has 8 valence electrons except for the hydrogen. Hydrogen is just too small to have 8 valence electrons, so that's why hydrogen does not have 8 valence electrons. It can only have 2. But does my Lewis structure match the total number of valence electrons which I should have, which is, where's that calculator? Oh, I closed it. Which is 12. Let's see, 2, 4, 6, 8, 10, 12, 14. Oh no, 14 valence electrons, but I should only have 12. When that is the case, you need to do the following. You have to subtract some valence electrons. We're doing this by pairs, all right? So you should never have an odd electron out there except for an advanced problem. And I'll tell you when the problem is advanced. On this particular homework assignment, there is no such advanced problem. All right, now, so you need to take a pair off of one atom and take a pair off of another atom, and you have to increase the bond. So this needs to be a double bond. Oh, here it is. Bond type. Yeah, bond type. So I'm going to change this bond type to a double bond. Okay? Okay, so there we go. So what I did was I took off carbon's own pair of electrons and oxygen's own pair of electrons, and I had them share those electrons instead. So instead of this kid having his own candy, represented by 2 dots, and this kid having his own candy, represented by the 2 dots which were removed by me, I took away their candy and made them share that candy, which is represented by this extra line here. All right? So that's how you figure out if you need a double bond. And let's count the valence electrons here. 2, 4, 6, 8, 10, 12. Yes, the structure has 12 electrons, and the formula has 12 electrons. And so I'm done. That's how you do it. All right? That's about it. All the problems in this homework assignment are like that. Now, in your next homework assignment for Lewis structures, you'll have to learn about formal charges, and the problems are going to be a little bit harder. But not to worry. The Chem 101 app is pretty good at giving you help with that, because there's a formal charge button here, which I'll show you after I redraw this formaldehyde structure. Okay, so here's the formaldehyde structure. Right. So these are known as lone pairs. These dots, they are electrons which are not involved in the bonding. Now, I wanted to show you about the formal charge feature. So just by clicking on formal charge, I could see that the formal charges are all 0. You're going to see that in the next homework assignment. The next homework assignment, you're going to have to choose between two different kinds of Lewis structures for the same compound. Here, let me show you exactly what I mean. I'm just going to cram it into this video since you're here and I'm here, right? Let's pretend it wasn't H2CO. Let's pretend it was HClO. Let's pretend you were doing this. Yeah. Now, if you were doing this, if you were doing the formula HCClO, right? HCClO, which is hypochlorous acid, which is found in swimming pools. If you needed to draw the Lewis structure for that, how would you know that you should make the double bond here with the oxygen? How would you know that that is correct instead of making the double bond here? You know, I mean, suppose you took off the lone pair from this guy, right? And you kept the lone pair on the oxygen, right? How would you know? How would you know that this isn't correct? I mean, all the rules that we've used, that I've used so far for the H2CO structure, are honored when I draw the structure like this for hypochlorous acid. I'm sorry, this is not hypochlorous acid. HCClO is something different. Anyways, HCClO. How would you know that HCClO could not be drawn like this? None of the rules that I used for H2CO tell you that you can't have a double bond here, but you have to have it here instead. The way you know, and this is going to be relevant in the next homework assignment, not this one, is by clicking on formal charge. You see there's a 1 here and a -1 right there, if you look real carefully. That means this is not a good Lewis structure. If there is a way for you to draw this a different, with a different pattern of bonds that results in all 0 formal charges, then that is the correct Lewis structure and not this one. Of course, sometimes you're not going to have a choice. Sometimes there are no new patterns to try while following all the rules. But in this case, there is a different pattern to try. Of course, I can take off the one of the lone pairs from this oxygen and make this a double bond. And I could take off this double bond and give this back his own candy, or his own valence electrons, and you see all the formal charges here are 0. So that tells you that this is the correct Lewis structure. So one more time, you don't need to worry about the formal charges when you are doing this homework assignment, but you are going to need them in the next homework assignment. Okay? Thank you. This valence electrons button could be useful. It's not very useful in my opinion, but if you prefer to have someone else count the valence electrons around each atom, you could use this valence electron button. However, please do not try to add these numbers up. 8 plus 8 plus 8 plus 2 is not the total number of electrons in this structure. The total number of electrons in this structure is 2, 4, 6, 8, 10, 12, 14, 16, 18, is only 18. Whereas if you try to add up all these numbers, you would have had a 26. All right. So that's it. Thank you. Bye.